The universe is full of amazing things, but some objects are so strange they really stand out. Beyond the familiar stars and planets, there are oddities like the giant bubbles in our galaxy, the almost empty voids, and objects that seem to defy the laws of the universe. These unusual features challenge what we know and give us new insights into the universe. Join me as we journey through the strangest objects in the universe. Pulsar J 1748-2446 AD, the fastest spinning pulsar. Imagine a star spinning so fast that it defies what we thought was possible. Pulsar J 1748-2446 AD is that star. We call it the Whirlpool star, and it's the fastest spinning pulsar ever discovered, rotating an astonishing 716 times per second. To put that into perspective, that's faster than a helicopter's blades. This rapid spinning raises fascinating questions about the forces at play in the universe and makes the Whirlpool star one of the most extraordinary objects in space. To really understand the Whirlpool star, we need to first understand what a pulsar is. Pulsars are a type of neutron star, which are the incredibly dense cores left behind after massive stars explode in supernova. Neutron stars pack more mass than the Sun into an area about 20 kilometers across, roughly the size of a small city. The density is almost unimaginable. For example, a sugar cube-sized piece of neutron star material would weigh around 1 billion tons. What makes pulsars special is that they emit beams of radiation as they spin, much like how a lighthouse sends out beams of light. If one of these beams points towards Earth, we see it as a pulse of radio waves, which is where the name pulsar comes from. The Whirlpool star is located about 18,000 light-years from Earth in the Terzan 5 globular cluster. This area is a dense grouping of stars, many of which are some of the oldest in the universe. What makes this pulsar truly unique is its incredible spin rate. It rotates 716 times per second, far faster than any other pulsar discovered so far. If Earth spun that fast, one day would last less than a millisecond. The speed at which the Whirlpool star spins is not a coincidence. Over time, pulsars can speed up due to a process called spin-up. This happens when material from a nearby star falls onto the pulsar. As this material spirals toward the pulsar, it transfers energy, causing the pulsar to spin faster. It's through this process that the Whirlpool star achieved its mind-boggling spin rate. With the Whirlpool star spinning so quickly, a natural question arises: how can it stay intact without tearing itself apart? The answer lies in the extreme gravity of neutron stars. Neutron stars have some of the strongest gravitational forces in the universe. This immense gravity counteracts the centrifugal force that would otherwise rip the star apart as it spins. However, scientists believe that the Whirlpool star is nearing the maximum speed at which a neutron star can spin before breaking apart. This is called the breakup limit. The fact that this pulsar is so close to that limit gives researchers important insights into the extreme conditions that exist in space. The location of the Whirlpool star in the Terzan 5 globular cluster is also interesting. This cluster contains a high concentration of pulsars, making it one of the best places to study these objects. The reason behind this abundance of pulsars is likely the high density of stars in the cluster. In environments like this, stars interact more frequently, which can trigger the spin-up process. In other words, the dense surroundings of Terzan 5 create the perfect conditions for the formation of millisecond pulsars like the Whirlpool star. The discovery and study of the Whirlpool star wouldn't have been possible without advanced technology. Pulsars are detected using radio telescopes, such as the Parkes Radio Telescope in Australia. These telescopes are capable of picking up the faint signals emitted by fast-spinning pulsars, like the Whirlpool star. By measuring the timing of these pulses very carefully, astronomers can determine the exact spin rate of the pulsar. But these observations aren't just cool facts. They also allow scientists to test some of the most fundamental theories in physics. Pulsars like the Whirlpool star provide a natural laboratory for testing Einstein's theory of general relativity, especially in extreme conditions where gravity is incredibly strong. The whirlpool star is not just remarkable because of its speed, it's also a tool for scientists to push the boundaries of physics. The extreme conditions around pulsars like this allow researchers to study the behavior of matter under enormous pressure and the effects of gravity in ways that can't be replicated on Earth. The hope is that with future technology, like the upcoming Square Kilometre Array, SKA, even faster pulsars could be discovered. This would open up even more possibilities for understanding the universe's most extreme conditions, and possibly even provide clues about the nature of matter itself. This pulsar also highlights the broader significance of pulsar research in general. Pulsars like the whirlpool star help scientists explore fundamental questions about the universe. These stars are natural laboratories for studying the most extreme environments imaginable, from the intense gravitational fields to the extreme densities of matter. Just as we've learned from observing phenomena like the brightest quasars, where massive black holes drive the formation of jets of energy, and Sagittarius A*, the supermassive black hole at the center of our galaxy, studying the whirlpool star, offers us a window into understanding how the universe works on a grand scale. Each discovery like this brings us one step closer to piecing together the full picture of the cosmos. What makes the whirlpool star particularly exciting is that it pushes the limits of what we think is possible. As astronomers continue to observe and study these fast-spinning stars, we might find even more pulsars that challenge our understanding of the universe. Sagittarius A, the supermassive black hole at the center of the Milky Way. At the heart of our galaxy, the Milky Way, lies an enigmatic and powerful force, Sagittarius A, SGRA for short. This supermassive black hole has a mass over 4 million times that of the Sun, making it one of the most influential objects in our galaxy. But what exactly is a black hole? And how did we discover this invisible giant lurking at the core of our cosmic home? A black hole is a region in space where gravity is so intense that nothing, not even light, can escape. Black holes form when massive stars exhaust their fuel and collapse under their own gravity, creating an extremely dense point called a singularity. Surrounding the singularity is an event horizon, the boundary beyond which nothing can return. Black holes warp space and time, stretching the laws of physics to their limits. For scientists, they provide an unparalleled opportunity to explore these extreme conditions. Sagittarius A belongs to the class of supermassive black holes, monsters millions or even billions of times heavier than our Sun. It resides about 26,000 light-years from Earth in the constellation Sagittarius, nestled at the very core of the Milky Way. Despite its colossal mass, SGRA is relatively quiet. Unlike some black holes that actively consume nearby material and emit powerful radiation, SGRA is currently in a dormant phase. However, its gravity still dominates the center of the galaxy, controlling the motion of stars and gas in the surrounding region. Since black holes do not emit light, how did scientists discover the existence of SGRA? The answer lies in tracking the motion of stars around it. For decades, astronomers have used telescopes to observe stars near the Milky Way's center, noticing their incredibly fast orbits around an unseen object. This object, later identified as SGRA, has a gravitational pull so strong that it can only be explained by a supermassive black hole. One of the most famous stars in this region is S2, which completes an orbit around SGRA every 16 years. S2's path brought it dangerously close to the black hole, allowing scientists to observe the effects of SGRA's intense gravitational forces. Another star, S62, has an even faster orbit, taking just 9.9 years to circle the black hole, further confirming its presence. In 2022, the Event Horizon Telescope, EHT, gave us our first glimpse of SGRA, capturing an image that revealed the black hole's shadow surrounded by a glowing ring of gas. While the image might look blurry, it was a groundbreaking achievement, showing material heated to millions of degrees as it spiraled toward the black hole. This provided critical evidence of SGRA's existence and shed light on how matter behaves near the event horizon. While SGRA is not currently devouring large amounts of material, black holes like it play an essential role in the evolution of galaxies. In their active phases, supermassive black holes emit jets of energy that can influence star formation and shape the overall structure of the galaxy. These jets can either trigger or slow down the formation of new stars, acting as a kind of cosmic regulator. Despite its immense power, SGRA poses no threat to Earth. We are far enough away, 26,000 light-years, to avoid its pull, and even the stars closest to the black hole are in stable orbits. Rather than being a danger, SGRA offers a unique window into the mysteries of the universe, allowing scientists to study gravity, space, and time in one of the most extreme environments imaginable. The center of the Milky Way is far from a quiet place, though. It's a bustling region filled with stars, gas clouds, and other celestial objects. The Galactic Center, as it's known, is a dense area packed with stars in varying stages of life. Some are young and hot, while others are older and nearing the end of their cycles. Massive clouds of gas and dust also populate this region, some of which may one day collapse to form new stars. All of these objects are subject to the gravitational pull of SGRA, shaping their orbits and movements. Though SGRA is quiet for now, it holds the key to understanding how supermassive black holes shape the universe. Its story is far from over, and as we continue to develop more powerful tools, the secrets of this cosmic heavyweight will come further into view. As we study SGRA, we not only learn more about black holes, but also about the forces that have shaped galaxies like our Milky Way since the dawn of time. 3. C. 273. The brightest quasar. While stars may dominate the night sky, quasars, one of the most energetic and luminous objects in the universe, outshine them by an astronomical margin. 3C 273 stands out as the brightest quasar visible from Earth. Discovered in 1963, this extraordinary object is located in the constellation Virgo, approximately 2.4 billion light-years away. But what exactly is a quasar, and why does 3C 273, or as we often call it, the cosmic lighthouse, hold such a significant place in the history of astronomy? To understand the cosmic lighthouse, we need to first explore what a quasar is. A quasar, short for quasi-stellar radio source, is a highly energetic object located at the center of a galaxy, powered by a supermassive black hole. As gas and dust spiral toward this black hole, they heat up to extreme temperatures, releasing vast amounts of energy across the entire electromagnetic spectrum: light, radio waves, and X-rays. Quasars are so powerful that they can outshine entire galaxies, and the cosmic lighthouse is about 4 trillion times more luminous than our Sun. What makes the cosmic lighthouse even more remarkable is its place in history. It was the first quasar ever identified, marking a turning point in our understanding of the universe. In the early 1960s, astronomers detected unusual radio signals coming from what appeared to be star-like objects. However, these signals were far too powerful to come from ordinary stars. The breakthrough came when astronomer Martin Schmidt, along with his colleagues, discovered that the light from the cosmic lighthouse was redshifted, a sign that the object was moving away from Earth at an incredible speed. This redshift placed the cosmic lighthouse far outside our galaxy, revealing it to be a distant, active galactic nucleus, not just another star. Despite being over 2 billion light-years away, the cosmic lighthouse remains visible through telescopes because of its extreme brightness. The supermassive black hole at its core is actively feeding on surrounding material, generating immense energy that travels across the cosmos. This makes the cosmic lighthouse a crucial tool for astronomers studying distant galaxies and the early universe. Its brightness also allows scientists to map large-scale structures in the universe, helping us understand how galaxies are distributed across space. The discovery of the cosmic lighthouse's redshift was groundbreaking. Redshift occurs when light stretches to longer wavelengths as an object moves away from us, due to the expansion of the universe. The high redshift of the cosmic lighthouse showed that it was not only incredibly far away, but also one of the most powerful objects known. This finding changed our understanding of quasars, revealing that they are extragalactic objects located far beyond the Milky Way. Before the cosmic lighthouse, many believed that the universe was relatively small, but the identification of quasars showed that there were distant, powerful objects far beyond our galaxy dot. The cosmic lighthouse opened the door to the study of thousands of other quasars, each offering new insights into the behavior of supermassive black holes and the formation of galaxies. While the cosmic lighthouse's brightness is impressive, it's not just a celestial spectacle, it's a window into the early universe. By studying quasars like this one, scientists can gain a better understanding of how galaxies form and evolve. Quasars act like cosmic lighthouses, helping us map the far reaches of space and learn more about the large-scale structure of the universe. In popular culture, quasars like the cosmic lighthouse have sparked imaginations, often being depicted as mysterious and powerful objects in science fiction. While the cosmic lighthouse itself may not appear in many stories, the concept of quasars has influenced countless depictions of extreme cosmic phenomena. Pulsar B 1257+12, the pulsar with planets. Pulsars are already fascinating objects, but Pulsar B 1257+12, also known as the Lich pulsar, takes things to an entirely different level. It has its own planetary system. Yes, you read that right. This pulsar, located about 2,300 light-years away in the Virgo constellation, hosts planets in orbit around it. This groundbreaking discovery from the early 1990s wasn't just interesting for its own sake. It marked the first time planets were discovered outside our solar system. But how could planets possibly survive around a dead star, especially one as extreme as a pulsar? Let's first refresh what we know about pulsars. A pulsar is a type of neutron star formed when a massive star collapses after a supernova explosion. These collapsed cores are incredibly dense and rotate rapidly, emitting beams of radiation as they spin. These beams sweep across the sky like a lighthouse, which is why we detect them as pulses when they pass by Earth. What makes the Lich pulsar particularly special, however, are the planets orbiting it. Pulsar B 1257+12 A, B, and C dot. These planets range in size from slightly smaller to slightly larger than Earth, but that's where the similarities to our home planet end. Imagine standing on one of these distant planets. Instead of a warm, life-giving star like our Sun, you'd be looking at a tiny, fast-spinning point of light, bombarding your planet with high-energy radiation. Solar flares? Those would seem mild in comparison to the constant streams of deadly particles coming from the pulsar's powerful magnetic field. Living on these planets would be impossible for any life as we know it. No atmosphere, no protection from radiation, just constant exposure to the pulsar's intense energy. The real mystery, however, is how these planets came to be in the first place. After all, pulsars form after a star has exploded in a supernova, which we would assume would destroy any nearby planets. So how are these planets still here? Or did they somehow form after the supernova? There are two main ideas about how this might have happened. The first theory suggests these are second-generation planets, formed from the debris left over after the explosion. In this scenario, the supernova's aftermath provided the materials to build new planets around the pulsar. The second theory suggests that the planets may have existed before the explosion and somehow survived the incredible forces of the supernova event. Whichever theory is correct, the Lich pulsar shows that planetary systems can arise or survive in places we wouldn't expect. These planets also make us rethink how common planetary systems might be across the universe. If planets can exist around something as intense and hostile as a pulsar, could there be other surprising planetary systems out there waiting to be found? Let's take a closer look at the 3 planets orbiting the Lich Pulsar. Pulsar B 1257 plus 12b and c are similar in size to Earth, but they orbit much closer to the pulsar, at distances comparable to Mercury's orbit around the Sun. Even though they are roughly Earth-sized, these planets are lifeless, rocky worlds stripped of any atmosphere due to the pulsar's constant radiation. The smallest of the 3, Pulsar B 1257 plus 12a, is about the size of our Moon, and orbits even closer to the pulsar, meaning it's exposed to even more extreme conditions. The discovery of these planets was made possible by using a technique called pulsar timing. This method involves measuring the tiny changes in the pulsar's spin caused by the gravitational pull of the orbiting planets. These slight timing variations gave scientists the clues they needed to detect these planets. This was a revolutionary moment in the search for exoplanets and helped pave the way for the discovery of many more planets outside our solar system in the years that followed. The existence of planets around a pulsar like the Lich Pulsar also expands our thinking about where we might find planets in the universe. Before the discovery of this system, most efforts to find exoplanets focused on stars that were more like our Sun. The planets of the Lich Pulsar, however, show that planets can exist around all kinds of stars, even those that have already died and turned into neutron stars. This finding broadened the scope of where we search for planets and deepened our understanding of how planetary systems form and evolve. The extreme environment of the Lich Pulsar also brings up a big question. Could life ever exist here? The conditions on the surface of these planets are far too hostile for life as we know it. Constant radiation, no atmosphere, and extreme temperatures make it an inhospitable place. But some scientists wonder if life might be able to survive underground, shielded from the pulsar's radiation. On Earth, we've found life thriving in some of the most extreme environments imaginable, such as deep-sea hydrothermal vents and radioactive waste zones. Could something similar happen on planets like these, where life might exist hidden away beneath the surface? The Lich Pulsar and its planets challenge our assumptions about where and how planets can exist. Just as other strange cosmic objects like the Bootes Void and Sagittarius A asterisk push the limits of what we think is possible, this pulsar system shows that the universe is full of surprises. From planets orbiting dead stars to the discovery of the brightest quasar, the Lich Pulsar expands our understanding of the variety of planetary systems that could exist in the cosmos. The extreme and unusual nature of the Lich Pulsar's planetary system makes it a captivating object of study. As we continue to learn more about this pulsar and other systems like it, we may find that there are even more bizarre and unexpected places where planets exist, maybe even in environments we would have thought impossible. Could there be other pulsars out there with their own planetary systems waiting to be discovered? The Lich Pulsar is a reminder that the universe is far stranger and more complex than we might have ever imagined, and it leaves us wondering what other cosmic oddities are still out there, waiting to be found. SGR 1806-20, the strongest magnetar. After exploring the strange planets orbiting pulsars like Pulsar B 1257 plus 12, let's push the limits even further and dive into something far more extreme, a magnetar. Specifically, the cosmic cannon. This magnetar, located about 50,000 light-years away in the Sagittarius constellation, is not just any magnetar. It holds the title of the most powerful one we know of, with a magnetic field that's a quadrillion times stronger than Earth's. If pulsars are intense, magnetars like the cosmic cannon take the concept of extreme to a whole new level. But before we get into what makes the cosmic cannon so extraordinary, let's break down what a magnetar actually is. Magnetars are a type of neutron star which are already incredibly dense remnants of massive stars that have exploded in supernovae. But unlike regular neutron stars, magnetars have unbelievably strong magnetic fields. The magnetic force of a magnetar, like the cosmic cannon, is so powerful that if you got anywhere within 1,000 kilometers of it, the magnetic field would distort the very atoms in your body, making normal biological processes impossible. Even from a distance of 100,000 miles away, the magnetar's magnetic field could wipe data from every credit card on Earth. That's how strong we're talking. Now, the cosmic cannon isn't just dangerous in theory. This magnetar is famous for producing one of the most powerful bursts of energy ever recorded. On December 27, 2004, it unleashed a massive gamma-ray burst, so strong that it even affected Earth's ionosphere, disrupting our planet's atmosphere for a brief moment. That's right, a star 50,000 light-years away had an effect on Earth. The burst released more energy in a fraction of a second than our Sun generates in 100,000 years. Just imagine, if this magnetar were closer, say only 10 light-years away, that burst could have stripped away Earth's atmosphere entirely, eradicating life as we know it. Where does all this power come from? The energy released by magnetars, like the cosmic cannon, is the result of starquakes. These are essentially shifts or cracks in the surface of the magnetar, caused by its immense magnetic forces. When these quakes happen, they release gamma rays and X-rays, some of the most energetic forms of light we know. The 2004 burst from the cosmic cannon gave scientists an incredibly rare opportunity to study the power of magnetars in action, and raised questions that still linger today. Could a similar burst occur much closer to Earth? And if so, how catastrophic would it be? Like pulsars, magnetars form from the remnants of stars that once shone brightly. After a supernova, what's left behind is a core made almost entirely of neutrons, which then becomes a neutron star. But for a magnetar to form, the conditions during the collapse must be even more extreme. Scientists think magnetars are born when the original star spins extremely fast as it collapses, creating an ultra-powerful magnetic field in the process. Not every neutron star becomes a magnetar, which is part of what makes them so rare and fascinating. Magnetars, like the cosmic cannon, don't last as long as regular neutron stars or pulsars. While a pulsar can keep spinning and emitting radiation for billions of years, a magnetar's intense magnetic field weakens over time. Magnetars typically remain active for about 10,000 years before they settle down and become more like regular neutron stars. The cosmic cannon is still in its highly active phase, which is why it continues to emit powerful bursts and magnetic activity. The 2004 event wasn't just an exciting burst of energy, it was a window into understanding some of the most extreme forces in the universe. Much like how the discovery of planets around Pulsar b 1257+12 expanded our ideas about where planets can form, magnetars, like the cosmic cannon, force us to reconsider the limits of stellar magnetic fields and cosmic energy. Scientists hope that by studying these rare events, we can learn more about how these powerful stars function, and in turn, gain insight into the fundamental forces that shape the universe. This brings us to a question that keeps coming up in these extreme environments. Could any form of life survive here? On the planets orbiting Pulsar b 1257+12, we at least entertained the possibility of life existing underground, shielded from the radiation. But around a magnetar like the cosmic cannon, it's hard to imagine anything surviving. The combination of extreme radiation, high energy bursts, and incredibly strong magnetic forces would make any nearby planets utterly inhospitable. Still, life has surprised us before, like the resilient microorganisms we found thriving in deep-sea volcanic vents and radioactive zones on Earth. Could something similar happen around a magnetar? It might seem far-fetched, but we've learned not to rule anything out when it comes to life in the universe. The cosmic cannon and other magnetars demonstrate just how varied and extreme cosmic objects can be. From gamma-ray bursts, powerful enough to affect planets light-years away, to magnetic forces that can twist atoms and molecules, Magnetars push the boundaries of what we thought stars could do. Each discovery like this doesn't just add to our knowledge, it forces us to rethink what's possible in the universe. Much like the strange pulsar planets of PSRB 1257+12 challenge our understanding of planetary systems, the cosmic canon challenges our concept of stellar remnants and the forces they can unleash. The immense power of the cosmic canon raises new questions with each new discovery. Could another gamma-ray burst, as powerful as the one in 2004, be lurking in the near future? What if it happens closer to Earth? The answers may not be comforting, but they certainly keep us on the edge of our seats, wondering what other extreme forces are at play in the universe. US 708, the Hypervelocity star. US 708, a hypervelocity star, is unlike anything we typically observe in our galaxy. It's not just far away, 30,000 light-years from Earth in the Centaurus constellation, but it's moving at a speed that truly boggles the mind. Most stars in the Milky Way drift along at speeds of 20 to 30 kilometers per second, but US 708, it's rocketing through space at an incredible 1,200 kilometers per second. Imagine a star zooming through the galaxy at roughly 4.3 million kilometers per hour. It's not just fast, it's one of the fastest moving objects we know of in the universe. What could propel a star to such outrageous speeds? To understand that, we need to explore how hypervelocity stars, like US 708, get their extreme velocities. These stars aren't born traveling this fast. Instead, their speed is often the result of intense and violent cosmic events. In the case of US 708, the story likely begins with it orbiting another star. This kind of binary system is pretty common in the universe, where two stars are gravitationally locked in an orbit around each other. But this binary didn't have an ordinary ending. As these two stars danced around each other, they likely ventured too close to a supermassive black hole. Black holes, especially the colossal ones at the centers of galaxies, like Sagittarius A* in the middle of the Milky Way, possess an overwhelming gravitational force. When a star gets too close, this force can tear them apart, or in US 708's case, send one of the stars hurtling into space at unimaginable speeds. This process, known as a gravitational slingshot, is what likely launched US 708 across the galaxy. Picture a slingshot launching a pebble. The tension builds up, and when released, the pebble shoots off at high speed. The same principle applies, except on a far grander scale. Instead of being flung a few meters, US 708 was catapulted into the cosmos at 1,200 kilometers per second. It's as if the black hole pulled back a cosmic slingshot and sent the star flying. The speed US 708 gained from this encounter is nothing short of incredible. Hypervelocity stars like this are rare, making US 708 a particularly important object for astronomers. By studying it, we can learn more about how stars interact with supermassive black holes. These interactions can tell us a lot about the environments near black holes, where gravity behaves in extreme ways, warping space and time itself. What's fascinating is that US 708 is still moving away from us. Unlike stars bound to the Milky Way by its gravitational pull, US 708 is likely on a one-way trip out of the galaxy. With a velocity like that, it won't slow down. In fact, it's expected to escape the Milky Way entirely, becoming a nomad star, drifting alone through intergalactic space. It's a remarkable fate for any star, escaping the pull of an entire galaxy and traveling alone through the vast emptiness between galaxies. But how did astronomers first discover US 708? It was back in 2005, during the Sloan Digital Sky Survey, that the star was initially identified. What stood out was its unusual speed. It was moving much faster than any star previously seen, and that caught the attention of scientists. With more detailed observations, they realized this wasn't just any fast star. US 708 was one of the fastest stars ever recorded. Hypervelocity stars like US 708 are rare, but incredibly valuable for scientists. By observing their movement, astronomers can better understand the dynamics of the Milky Way and the forces at play. For instance, these stars help us study the incredible gravitational power of black holes, especially the supermassive ones lurking in the centers of galaxies. If a star like US 708 can be flung across space by a black hole's gravity, it shows just how powerful and far-reaching these gravitational forces are. But these high-speed stars also raise more questions. What happens to them after they've been ejected from their galaxies? US 708 is on a journey that may never end. As it moves farther away from the Milky Way, it may drift through intergalactic space, leaving behind its home galaxy forever. And what's even more intriguing is that US 708 isn't alone in this. There may be other hypervelocity stars on similar paths, flung out of their galaxies by the violent forces of black holes. Hypervelocity stars also help scientists study the structure of the universe itself. By analyzing stars like US 708, astronomers can get a better sense of how galaxies are shaped and influenced by the massive objects within them. Black holes, after all, play a critical role in shaping galaxies. They influence the motion of stars and the overall structure of the galaxies they reside in. Stars like US 708 are living proof of the kind of extreme dynamics black holes can produce. But could there be even faster stars than US 708? While it holds the record now, the universe is vast and full of surprises. It's possible that somewhere out there, another hypervelocity star is moving even faster, waiting to be discovered. These stars could reveal new insights about the extreme conditions that lead to such incredible speeds, pushing our understanding of stellar dynamics even further. Beyond their speed, hypervelocity stars offer a glimpse into the long-term fate of stars and galaxies. The fact that US 708 is leaving the Milky Way brings up questions about the future of stars in our universe. As galaxies evolve and black holes continue to shape their surroundings, will more stars be ejected into intergalactic space? What happens to a star when it no longer belongs to a galaxy? These are questions that scientists are only beginning to explore, and US 708 is at the heart of that investigation. This star's story connects to broader themes in astronomy. We've already delved into other extreme objects, like pulsars, black holes, and supernovae. US 708 adds another layer to our understanding of cosmic forces. While pulsars represent the end of life for some stars, and black holes show the ultimate destruction of matter, hypervelocity stars show the aftermath of close encounters with these destructive forces. In a way, US 708 is a survivor, having escaped the clutches of a black hole, but now paying the price by hurtling alone through space. Sirius B, the superdense white dwarf. Let's dive into one of the universe's most fascinating objects, Sirius B. This white dwarf is located in the constellation Canis Major, and it might not seem like much at first glance. After all, it's much smaller and dimmer than its more famous companion Sirius A, the brightest star in our night sky. But don't let its faint glow fool you. Sirius B holds some remarkable secrets about the life and death of stars. To understand why Sirius B is so interesting, we need to start with its discovery. In 1844, a German astronomer named Friedrich Bessel noticed something odd. He was studying Sirius A, but he realized the star had a slight wobble in its movement. What could be causing this? Bessel predicted that another unseen object was orbiting Sirius A, and he was right. This wobble led to the discovery of Sirius B, a white dwarf that was gravitationally pulling on its larger companion. It was one of the first times astronomers had observed a hidden object in space through its gravitational influence rather than its light, a technique that would become crucial in the discovery of many other cosmic phenomena. But what exactly is a white dwarf? White dwarfs are the remnants of medium-sized stars, like our Sun, that have burned through their nuclear fuel. After a star like this exhausts its energy, it sheds its outer layers, leaving behind a dense, hot core. This core is what becomes a white dwarf. Sirius B is a perfect example of this process. Once it was a massive star, much bigger and brighter than it is now. But as it aged, it reached the end of its life cycle, shedding its outer layers and shrinking down into the dense white dwarf we see today. Speaking of density, let's talk about just how tightly packed Sirius B is. Even though it's roughly the size of Earth, it has almost the same mass as our Sun. That's a mind-boggling amount of matter crammed into such a small space. To put it in perspective, a single teaspoon of material from Sirius B would weigh several tons. This incredible density results in surface gravity 350,000 times stronger than what we experience on Earth. Imagine standing on Sirius B. If you weigh 70 kilograms here, you'd weigh over 24 million kilograms there. It's a gravity so intense that it's nearly impossible to fathom. Now, if you look at Sirius A, its bright, shining light might make Sirius B seem insignificant. But the truth is, long ago, Sirius B was the star that outshone Sirius A. Before it became a white dwarf, it was much larger and more luminous than its companion. Over time, however, as Sirius B aged and lost its outer layers, Sirius A became the brighter of the two. This reversal of roles is a reminder of just how dynamic the universe can be. Stars are constantly evolving, and the brightest ones today could eventually fade into faint remnants like Sirius B. Although Sirius B is no longer burning through nuclear reactions, it remains incredibly hot. Its surface temperature is over 25,000 degrees Celsius. Even though it's been cooling for billions of years, this heat is a leftover from its past, when it was a much larger star. While it no longer generates new energy, this residual heat keeps it glowing faintly as it slowly cools. This process of cooling over billions of years is a defining feature of white dwarfs, and Sirius B gives astronomers a chance to study this phase of a star's life up close. One of the most interesting aspects of Sirius B's history is its past as a red giant. Before collapsing into a white dwarf, Sirius B expanded into a red giant as it neared the end of its life. During this phase, it was likely surrounded by a glowing shell of gas and dust, a planetary nebula. Planetary nebulas are the outer layers of a dying star ejected into space, leaving behind the dense core. Today, that nebula is long gone, but the memory of it lives on in the remnants of Sirius B. Even though Sirius B has reached the final stages of its life, its existence is still incredibly important for astronomers. By studying it, scientists learn more about the life cycles of stars and the evolution of the universe. White dwarfs like Sirius B give us a rare look into what will eventually happen to stars like our Sun. In billions of years, our Sun too will shed its outer layers and leave behind a white dwarf. Observing Sirius B helps us understand what that future might look like. One of the biggest mysteries surrounding Sirius B is whether it ever hosted planets. Could planets have orbited Sirius B before it became a white dwarf? While no planets have been discovered, it's possible that any orbiting bodies were destroyed or flung out of the system when Sirius B expanded into a red giant. This raises intriguing questions about the fate of planets in other star systems. If stars like Sirius B had planets, what happened to them? And could any planet survive such a dramatic transformation? Looking forward, what will happen to Sirius B in the distant future? We know that white dwarfs eventually cool down and fade into what's known as a black dwarf, a cold, dark remnant of a star. But here's the catch. The universe is still too young for any black dwarfs to exist. It will take trillions of years for white dwarfs like Sirius B to cool completely. So, while we can predict Sirius B's future, it's a future that's still many billions of years away. The existence of Sirius B also connects to larger cosmic questions. For instance, how does the presence of white dwarfs impact the movement of stars within galaxies? In the case of Sirius B, its gravitational pull affects Sirius A, causing slight changes in its orbit. This kind of interaction is happening all over the universe as unseen forces tug on visible stars, altering their paths. Studying Sirius B helps astronomers better understand these dynamics and how galaxies evolve over time. What about its relation to other strange objects in the universe? In previous discussions, we've explored the incredible speed of hypervelocity stars like US 708 and the intense magnetic fields of neutron stars. While these objects might seem vastly different from Sirius B, they all share one thing in common. they help us understand the extremes of physics. Whether it's the incredible density of a white dwarf, the speed of a hypervelocity star, or the crushing gravity of a neutron star. These objects push the boundaries of what we know about the universe. And this leads to one final question. What happens when two white dwarfs collide? While it won't happen in the case of Sirius A and B, the merger of two white dwarfs can lead to a spectacular cosmic event, a Type Ia supernova. This explosion occurs when the combined mass of the two white dwarfs exceeds a critical limit, causing a runaway nuclear reaction. While Sirius B's future doesn't include such a dramatic end, its existence gives us insight into how such events might occur elsewhere in the universe. SN 1998 BW, the Eddington Limit Star. Stars live out their life cycles in dramatic fashion, and few cosmic events highlight this better than SN 1998 BW, also known as the Eddington Limit Star. Its explosion wasn't just any supernova. It marked one of the most extraordinary occurrences ever witnessed by astronomers. At its core, the Eddington Limit Star defies traditional limits and shines a light on the mysterious forces at play during the death of massive stars. The first time the Eddington Limit Star drew significant attention was in 1998, when it was linked to a gamma-ray burst, GRB 980425, something extremely rare. Gamma-ray bursts are among the most energetic events known to science, and this was one of the few instances where a supernova was observed almost simultaneously. That coincidence became a catalyst for a deeper investigation, raising key questions about the relationship between these intense bursts of energy and the violent demise of stars. To appreciate what makes the Eddington Limit Star so special, it's crucial to understand the concept of the Eddington luminosity. This is essentially a star's breaking point, the threshold at which the radiation it emits is so intense that it counteracts its own gravitational forces. If a star surpasses this limit, it can no longer hold itself together. That leads to extreme consequences, like mass ejections, or, as in this case, a catastrophic explosion. The star behind the Eddington Limit Star was far from ordinary. Massive in size, it was approaching the final stages of its life. After burning through its fuel, the balance between nuclear fusion and gravity began to break down. Without enough energy to support its core, the star's outer layers were violently expelled into space. But what made this supernova different was the sheer amount of energy it released, far more than a typical supernova, propelling the Eddington Limit Star into the category of a hypernova. Astronomers weren't just surprised by the brightness of the Eddington Limit Star. They also found that it unleashed jets of material that moved at incredible speeds, likely responsible for the accompanying gamma-ray burst. These jets are a telltale sign of powerful stellar collapses, especially when the core of a star implodes, forming a black hole. Although the gamma-ray burst linked to the Eddington Limit Star was weaker than many others, the connection between the two events was undeniable and offered a unique opportunity to study both phenomena together. The energy levels of the Eddington Limit Star were far beyond what scientists had anticipated. Typical supernovae are already some of the most energetic events in the cosmos, but this one exceeded expectations by a wide margin. At its peak, the luminosity of the Eddington Limit Star shattered the Eddington luminosity, demonstrating that stars can push beyond their theoretical limits in certain extreme conditions. This discovery fueled new research into the collapse of massive stars and how the balance of forces within them can break down in such an explosive fashion. As astronomers examined the aftermath of the Eddington Limit Star, they gained valuable insights into the type of star that created it. Based on the data, scientists believe the original star was massive, several times the size of our Sun. By the time it exploded, all that remained was a dense core which likely collapsed into a black hole after ejecting its outer layers. This process, the transformation of a massive star into a black hole, is one of the most important phenomena in stellar evolution. The Eddington Limit Star wasn't just a lesson in how stars die, but also in how they communicate their death across the universe. Gamma-ray bursts are often regarded as the cosmic lighthouses of the universe, and the Eddington limit star's simultaneous gamma-ray burst provided evidence of how these two phenomena can be linked. While not all supernovae produce gamma-ray bursts, and not all gamma-ray bursts are tied to supernovae, when the two coincide, it offers rare insights into the extreme conditions surrounding these catastrophic events. The relationship between the Eddington luminosity and the Eddington limit star is one of the event's most fascinating aspects. As stars evolve and push the boundaries of their natural limits, they create new pathways for astronomers to understand the universe. The Eddington limit star serves as a powerful reminder that even the most established rules in astrophysics, like the Eddington limit, can be broken under the right conditions. The jets of material ejected by the Eddington limit star likely played a key role in its accompanying gamma-ray burst. These jets, moving at nearly the speed of light, are thought to be one of the reasons gamma-ray bursts are so energetic and powerful. They provide a glimpse into the chaotic and violent processes that occur during a star's death, revealing a world of cosmic forces that challenge our understanding of physics. The Red Square Nebula. The Red Square Nebula is one of the most visually striking objects in the cosmos, capturing attention with its unusual geometric shape. Located around 2,000 light-years away in the constellation Scorpius, this planetary nebula stands out for its square-like appearance, a rarity in the universe. Planetary nebulae, including the Red Square Nebula, are the remnants of stars that have reached the end of their life cycles. When a star similar to our Sun exhausts its nuclear fuel, it expels its outer layers into space, leaving behind a hot core. This core, known as a white dwarf, emits intense ultraviolet light, causing the surrounding gas to glow. This process creates the nebula that we observe. Most planetary nebulae appear round or irregular because the gas expelled by the dying star is often ejected in all directions. However, the Red Square Nebula's shape is notably different. It appears square or rectangular, but this is more about our viewing angle than the nebula's true shape. The actual structure of the nebula is more diamond or kite-like. This apparent square is an optical illusion caused by how the gas clouds are arranged and how light passes through them. The nebula's distinctive form is a result of complex forces at play. The central star's strong magnetic fields and rotational dynamics influence the ejected gas, shaping the nebula into its unique appearance. As the star sheds its outer layers, these magnetic fields and the star's rotation can create intricate patterns in the surrounding gas. The Red Square Nebula was first identified in 2004 using the Very Large Telescope (VLT) in Chile. This discovery allowed astronomers to study a planetary nebula with such an unusual shape in detail. Observations revealed concentric rings and gas jets around the central star, contributing to its unique look. These features are a direct result of the star's intense ultraviolet radiation and the magnetic forces at work. The central star of the Red Square Nebula is a hot and massive white dwarf. It plays a crucial role in shaping the nebula. The star's radiation ionizes the surrounding gas, making it glow brightly. This radiation also affects the nebula's structure, creating the striking patterns that define its appearance. Studying the Red Square Nebula offers valuable insights into the life cycle of stars. It helps astronomers understand how stars end their lives and how their remnants interact with their environment. The unique shape of the nebula also sheds light on the role of magnetic fields in shaping these final stages of stellar evolution. The Red Square Nebula's structure highlights the complex interplay of cosmic forces. The combination of the star's radiation and magnetic fields creates intricate and unexpected shapes. This nebula serves as a reminder of the variety and complexity of celestial objects. Dark energy, the cosmic force driving expansion. In 1912, astronomer Vesto Slipher noticed that distant galaxies were redshifted, meaning they were moving away from Earth. This observation was one of the first clues hinting at something strange about the universe's expansion. While its full implications weren't understood at the time, Slipher's discovery would later connect to one of the most puzzling concepts in modern cosmology: dark energy. Fast forward to the late 20th century, when the Hubble Space Telescope provided astronomers with a breakthrough. Studying distant Type Ia supernovae, researchers found these exploding stars appeared dimmer than anticipated. This dimming wasn't just a small anomaly, it suggested that the universe's expansion was speeding up rather than slowing down as previously assumed. Astronomers were stunned. Everything we thought we knew pointed to gravity eventually pulling the universe back together. However, these supernovae revealed the opposite. Something unknown, later called dark energy, was driving the universe apart faster and faster. This marked a dramatic shift in our understanding of the cosmos. But how do we even know dark energy is real? Beyond supernova observations, another key piece of evidence comes from the cosmic microwave background, CMB, the faint afterglow of the Big Bang. The CMB acts as a snapshot of the universe when it was only about 380,000 years old. It provides clues about the universe's shape, age, and rate of expansion. Detailed studies of the CMB indicate that the universe's expansion started accelerating billions of years ago. This supports the idea that an unknown force, now known as dark energy, is at play. Galaxy clusters also help unravel the mystery of dark energy. These massive structures, which contain thousands of galaxies, are held together by gravity. However, the way these clusters are distributed throughout space suggests that something is pushing against gravity. Dark energy, it seems, isn't just expanding the universe, it's actively preventing galaxy clusters from forming at the rate they should. In fact, research has shown that galaxy clusters are more widely spaced today than they would be if gravity were the only force at play. To understand how this works, think about the large-scale structure of the universe. It's made up of filaments, clusters, and vast voids. These voids are essentially empty spaces between galaxies, and they're growing. Dark energy isn't just pulling galaxies apart, it's stretching the very fabric of space, creating more emptiness between cosmic structures. The Sloan Digital Sky Survey, which has mapped millions of galaxies, has provided key evidence of this expansion, revealing that voids are expanding more rapidly than previously thought. Dark energy's influence goes beyond galaxies and voids. It even impacts time itself. Recent research suggests that as the universe expands, it stretches the fabric of space-time. This stretching may be affecting the flow of time on a cosmic scale. For instance, time dilation, a phenomenon observed in distant supernovae, shows how time appears to slow down in areas where dark energy has the most significant impact. This observation not only deepens the mystery surrounding dark energy, but also hints at its profound influence on the universe's structure and the flow of time. But dark energy doesn't just influence the present, it holds the key to the future of the universe. If the current rate of acceleration continues, galaxies will keep moving further apart, and cosmic structures will drift beyond each other's reach. Stars will eventually burn out, leading to what scientists call the Big Freeze. This scenario envisions a universe that becomes darker and colder as time goes on, with galaxies becoming more isolated in the vast expanse of space. There's another, more extreme possibility, known as the Big Rip. This theory suggests that dark energy's effects could grow stronger over time. If that happens, it wouldn't just push galaxies apart, it could tear them apart. Over time, dark energy could become so powerful that it would overcome gravity, tearing apart galaxies, stars, planets, and even atoms. The universe would be ripped apart at the most fundamental level, leaving behind only an empty void. On the flip side, some scientists suggest that dark energy's influence might balance out, leading to a more stable rate of expansion. In this scenario, galaxies would continue to move apart, but the rate of expansion would slow down, allowing stars to form and evolve more gradually. While this future wouldn't be as dramatic as the Big Rip, it would still mean a universe that slowly grows more isolated as galaxies drift apart. What's fascinating is that despite its profound effects, we still don't know what dark energy actually is. Could it be a new form of energy we've never encountered? Or does it represent something even more mysterious, perhaps linked to the nature of space-time itself? These are some of the biggest questions in modern cosmology, and researchers are racing to find answers. The ongoing study of dark energy is also pushing the boundaries of technology. Projects like the Dark Energy Survey and the upcoming Euclid Space Telescope are designed to map the universe in more detail than ever before, hoping to uncover new insights into how dark energy operates. These tools will allow astronomers to study billions of galaxies, providing a clearer picture of how the universe has evolved and how dark energy has shaped that evolution. Ultimately, dark energy connects to other cosmic phenomena in profound ways. Take, for example, hypervelocity stars. Stars that are moving through space at incredible speeds. While these stars are often ejected from galaxies due to gravitational interactions, the vast emptiness created by dark energy could allow them to travel even farther and faster. Similarly, the Bullet Cluster, a massive collision between two galaxy clusters, also provides indirect evidence for dark energy, showing that something is causing space to expand and making such large-scale collisions more widespread. Hoag's object, the Ring Galaxy. When Arthur Hoag stumbled upon a strange round object in the constellation Serpens in 1950, he thought he had found a planetary nebula. At first glance, it seemed like one, a glowing sphere of gas around a dying star. But deeper investigation revealed something much rarer and more fascinating, a nearly perfect ring galaxy. This discovery of what would later be called Hoag's object challenged common ideas about galaxy shapes. Rather than the familiar spirals or elliptical forms, here was a cosmic ring, bright with young blue stars surrounding an older yellow core, floating like a cosmic eye in the void of space. One of the most puzzling aspects of Hoag's object is that, unlike most known ring galaxies, it doesn't appear to have a companion galaxy nearby. Typically, rings form when two galaxies interact, their gravitational forces pulling stars and gas into these striking circular formations. But in Hoag's case, no such companion has been found. This isolated existence makes it stand out even more from other galactic formations. Its formation may have been far more peaceful and unique than the violent collisions we see in other galaxies. In fact, the stars within the ring are some of the youngest you'll find in a galaxy. These blue stars are just beginning to burn bright, but they contrast sharply with the older yellow core at the center. This age difference between the ring and the core adds to the galaxy's mystery. It suggests that something caused the outer ring to form well after the core had already settled into its quiet, stable state. But what kind of event could form a ring of stars without disturbing the core? This remains one of the key mysteries about Hoag's object. What's even more surprising is that Hubble's Space Telescope, with its ability to peer deep into space, revealed something else hiding in the background of this already mysterious galaxy. Far beyond the bright blue stars, there's a faint second ring, almost invisible to all but the most sensitive instruments. This discovery hints that the galaxy may have a more complicated past than we first thought. Could it have gone through multiple stages of formation, with one ring forming long after another? Or does this second ring represent an entirely different process at work, one that we haven't yet fully understood? What's especially intriguing is the fact that the core of Hoag's object, despite being surrounded by these energetic young stars, remains remarkably undisturbed. You'd expect such contrasting star populations to interact, gravitationally pulling at each other, creating distortions or even causing bursts of star formation. But none of this is seen here. The core and the ring appear to coexist without any apparent conflict, which raises the question, what kind of force or balance is keeping this galaxy stable? Adding to the mystery is how this ring galaxy is studied. Optical images are crucial in observing the sharp contrast between the core and the ring, helping astronomers map out the distribution of stars and gas within the galaxy. But it's not just about pretty pictures. Spectroscopy, a method that breaks down light into its various wavelengths, offers critical clues. By analyzing the light coming from different parts of the galaxy, scientists can pinpoint the ages of the stars, their chemical makeup, and even the rate at which new stars are forming. In the case of Hoag's object, this method shows a striking difference in the ages of the stars in the core and the ring. highlighting the starkly different environments within the same galaxy. As astronomers dig deeper, they've uncovered other features of Hoag's object that remain difficult to explain. One such puzzle is that there's no sign of a recent galactic collision or even the presence of a smaller satellite galaxy that could have triggered the formation of the ring. Most ring galaxies are formed when one galaxy passes through another, creating ripples of star formation as the gas and stars get pulled into a ring. But here, there's no evidence of such a dramatic event. Some theories suggest the ring could have formed from internal instabilities, where parts of the galaxy's own matter shifted over time, creating the striking structure we see today. One might wonder, how does this compare to other galaxies with rings? Most ring galaxies come with clear backstories, interacting with neighbors or crashing into other galaxies. Hoag's object lacks this clear backstory. It sits isolated, as if it formed in a bubble. That makes it stand apart from other cosmic structures like the bullet cluster or the immense forces of dark energy. While those phenomena tell stories of large-scale cosmic violence or the mysterious expansion of the universe, Hoag's object hints at a quieter, more serene process. Yet, its calm appearance doesn't make it any less mysterious. And here's a mind-bending thought. What if the ring isn't actually part of Hoag's object at all? Some astronomers have toyed with the idea that what we're seeing is a galactic illusion, where the ring is actually a separate galaxy far in the background, perfectly aligned with the core from our point of view. It's an unlikely but fascinating possibility that adds yet another layer to this puzzle. If true, it would mean that what we're observing is not a single unique structure, but an incredible cosmic coincidence where two unrelated galaxies appear to be one. While this remains speculative, it shows just how strange and unpredictable the universe can be. Equally puzzling is the fact that Hoag's object, with its seemingly disconnected parts, shows no signs of the gravitational tug-of-war we'd expect. In most galaxies, the gravitational forces between the core and the surrounding stars would create distortions or even chaos. Yet, in Hoag's object, both the core and the ring seem to exist in perfect harmony. Could this suggest the presence of an unknown force stabilizing the galaxy? Or does this point to a new type of galaxy formation process that we've yet to fully understand? The stars in the outer ring don't follow the usual paths seen in galaxies that have experienced major collisions or disruptions. Instead, they seem to have formed relatively quietly, without the usual cosmic drama. Tabby's star, the unusual dimming star. Tabby's star, also known as Chi C 8462852, stands out as one of the most puzzling stars ever discovered, showing behavior unlike anything astronomers typically observe. Though this star was first catalogued long ago, it wasn't until the Kepler Space Telescope started its mission that something truly strange was detected. Kepler's goal was to find exoplanets by watching stars dim when planets pass in front of them. But with Tabby's star, it recorded dimming events that were unpredictable and far deeper than what could be explained by a planet. This star's dimming pattern doesn't match the regular periodic dips seen in other stars with exoplanets. The light from Tabby's star drops by as much as 22%, which is extremely unusual. A planet's transit might cause a slight dimming, but nothing close to this level. What's even more baffling is that the dimming doesn't follow a set pattern. Sometimes the star dims for a few days. Other times, it stays dim for weeks or months. There's no regular cycle to follow, making it a mystery that has captured the attention of scientists around the world. The discovery of this strange dimming behavior isn't new. While Kepler's data brought it into focus, historical records show that the star has been gradually dimming for at least the past 100 years. Old star charts, including those from Harvard's collection dating back to the 19th century, reveal that Tabby's star has been slowly fading. This long-term dimming is unusual in itself, suggesting that something ongoing and persistent is affecting the star over time. One of the early ideas proposed to explain the strange dimming was that a large cloud of dust was passing between us and the star. If a dense cloud of interstellar dust blocked the star's light, it could account for the drop in brightness. However, this theory quickly ran into problems. Dust tends to emit infrared radiation, and when astronomers used infrared telescopes to look at Tabby's star, they didn't find enough heat to suggest that such a dust cloud existed. While many hypotheses have been considered, one theory that gained widespread attention in the media was the possibility of an alien megastructure, such as a Dyson sphere. A Dyson sphere is a hypothetical structure built by an advanced civilization to capture energy from a star. This idea sparked the public's imagination, but no solid evidence supports it. The lack of any clear signals from the star makes it unlikely that we're dealing with something built by extraterrestrials, though it's a possibility that remains fun to consider. Adding to the complexity is the fact that the star doesn't emit strong X-ray or ultraviolet radiation, which would be expected if it were experiencing some kind of extreme stellar activity. Many stars that show odd behavior also have strong X-ray emissions, which can point to flares or other magnetic events. But Tabby's star doesn't have any such signals. This rules out common causes like stellar flares or pulsations that often explain changes in brightness. An even more recent finding is that the star has been steadily dimming over the past century, but not in the way that other stars usually dim. The fading appears gradual and continuous, unlike the sharp drops in brightness caused by passing objects like planets or comets. This suggests that Tabby's star is undergoing some unique process, which could involve a combination of different factors rather than a single cause. There's another idea that hasn't gained as much attention, but offers an interesting possibility. Some researchers think that Tabby's star could be in the process of consuming a smaller companion star or planet. This process, known as stellar accretion, could cause unpredictable dimming as material falls into the star over time. If the star is slowly pulling in debris from a nearby object, it might explain why the dimming is so irregular and why we don't see the typical emissions associated with other dimming stars. Oumuamua, the interstellar visitor. Oumuamua was first noticed as it moved through our solar system on a path unlike anything astronomers had ever seen. Instead of behaving like typical objects such as asteroids or comets, it followed an eccentric trajectory, a clear sign that it came from beyond our solar system. This was the first direct evidence of an interstellar visitor, and it marked a monumental moment in our understanding of the universe. The way it moved was unexpected, and scientists quickly realized that Oumuamua wasn't following the patterns they had come to expect from cosmic objects formed in our solar system. The shape and speed of this object made it stand out, and as more data came in, the mystery surrounding it only deepened. It didn't take long before astronomers started speculating about the object's unusual shape. Most celestial bodies, like asteroids or comets, are roughly spherical or irregular in form, but Oumuamua was distinctly elongated, almost like a giant cigar tumbling through space. Its proportions, estimated to be about 800 meters long and only 80 meters wide, make it one of the longest objects ever recorded. But why would something so different from the usual objects we observe end up traveling through our solar system? Some scientists have proposed that this strange shape might be due to Oumuamua coming from a binary star system. In systems where two stars orbit one another, the gravitational forces are far more complex. It's possible that Oumuamua was ejected from one of these systems, its shape molded by the intense forces it encountered there. One of the most intriguing mysteries surrounding Oumuamua was its lack of a cometary tail. Typically, when a comet approaches the Sun, the heat causes the ice on its surface to sublimate, forming a bright tail of gas and dust. But as Oumuamua moved closer to the Sun, no such tail appeared, leaving scientists puzzled. One possible explanation for this is that Oumuamua's surface might have been made of hydrogen ice. If this were the case, the sublimation of hydrogen wouldn't produce a visible tail, even though it could still be responsible for some of the object's unexpected movements. This theory adds a new layer to the mystery of what Oumuamua is made of and how it behaves. Another puzzle arose as astronomers studied how Oumuamua moved. Objects in space usually follow predictable paths determined by gravity, but Oumuamua seemed to accelerate as it left the solar system, something that shouldn't have happened if it were merely coasting on the momentum it had when it first entered. Some proposed that this extra acceleration could be due to outgassing, where gases escape from a comet and give it a little push. But with no tail or visible signs of gas, the mystery deepened. Others thought it might be due to solar radiation pressure, the force exerted by sunlight. If Oumuamua were thin enough, sunlight could push it along, much like a sail catching the wind. But no one was expecting an object like this to behave in such a way. The story of Oumuamua doesn't stop with its peculiar shape and motion. Scientists have also explored where it might have come from, and one idea suggests it could have been a piece of a larger object that was shattered and ejected from its home star system. Some believe it may have come from the outer edge of an exoplanetary disk, a region similar to our Kuiper belt or Oort cloud, where debris from the formation of planets can still be found. If that's true, Oumuamua might offer us a glimpse of how planetary systems beyond our own evolve and interact. The ejection of such a fragment could have occurred due to large planets migrating in its original system, a process that astronomers believe has shaped the history of our own solar system. Another layer to this cosmic mystery involves Oumuamua's rotational motion. As it passed through our solar system, it wasn't just moving, it was tumbling end over end. This kind of spinning motion suggests that Oumuamua had undergone some serious gravitational stress before it arrived here. It may have passed close to a large object, such as a star, and been subjected to tidal forces that altered its shape and set it tumbling. This further supports the theory that Oumuamua might have come from a binary star system where such interactions are more common. The tumbling motion, combined with its strange shape, adds to the evidence that Oumuamua has had a chaotic history before making its way to us. The spectral analysis of Oumuamua revealed another interesting clue. Its surface didn't match the composition of any known comet or asteroid from our solar system. The reddish tint observed could be a result of space weathering, exposure to cosmic rays and interstellar dust over millions of years. This weathering process could have altered Oumuamua's surface chemistry, providing further evidence that it's been traveling through the galaxy for a long time, perhaps even millions or billions of years. These findings make Oumuamua not just an object of curiosity, but a relic of a distant and perhaps very ancient star system. Despite all the scientific data collected, one of the more imaginative theories gained traction in the public eye: the idea that Oumuamua might be an alien probe. Its strange shape, high speed, and unexpected acceleration led some to wonder whether it could be a spacecraft sent by an advanced civilization. While most scientists have dismissed this idea due to a lack of solid evidence, the mere suggestion speaks to the extraordinary nature of Oumuamua and how little we still understand about interstellar visitors. Yet, the absence of any direct signs of artificial construction, such as radio signals or regular maneuvering, has led researchers to conclude that it is most likely a natural object, albeit an extremely unusual one. Fermi bubbles, the galactic mysteries. The Fermi bubbles, located above and below the Milky Way's center, are still puzzling researchers today. Studies now suggest these gigantic bubbles might be younger than previously thought, possibly forming less than 10 million years ago. That's very recent in the life of a galaxy. With their relatively new existence, it challenges earlier ideas that structures like these take hundreds of millions of years to form. One intriguing idea involves a past event linked to our galaxy's supermassive black hole, Sagittarius A*. Sagittarius A* is quiet now, but it may not always have been. Some scientists propose the Fermi bubbles are leftovers from a massive explosion, a bipolar jet from the black hole. During periods of high activity, this black hole might have shot out material, now left hanging as enormous bubbles. This connection opens up more questions about the once chaotic past of our galactic center. The gamma rays pouring out of the Fermi bubbles are only part of the story. These structures also give off something less known: non-thermal radio waves. These waves, generated by high-energy particles interacting with the bubble's magnetic fields, hint at shock waves rumbling through the bubbles. The discovery of such intense non-thermal radio emissions has taken scientists by surprise, as this process is rarely observed on such a large scale in any galaxy. Scientists also found polarized light within these bubbles. The way the light is polarized shows how the magnetic fields inside the bubbles are arranged. Instead of simple, calm magnetic lines, the fields are chaotic and turbulent, adding another piece to the mystery of how these bubbles formed. the bubble's structure goes even deeper. X-ray observations have shown shockwaves racing through the Fermi bubbles. These waves suggest a violent origin, potentially driven by past black hole eruptions or intense bursts of star formation. The shockwaves are likely linked to high-energy explosions that occurred when the bubbles first formed, giving us a hint of how powerful the processes shaping the Milky Way once were. One of the more interesting discoveries involves electron-positron annihilation within the bubbles. When electrons meet their antimatter counterparts, positrons, they annihilate each other, releasing energy. Researchers have found traces of this process inside the bubbles. These interactions could be linked to the black hole's energy output or even to more exotic physics, possibly related to dark matter. The symmetry of the Fermi bubbles is another strange feature. Above and below the Milky Way's plane, the bubbles stretch out almost perfectly in both directions. Given the chaotic environment at the center of our galaxy, it's surprising that these massive structures don't show more irregularities. This symmetry makes them even more intriguing, as such large features usually show distortion, especially considering the activity going on near Sagittarius A*. One of the most surprising findings is the strength of the magnetic fields inside the Fermi bubbles. They're much stronger than expected, playing a key role in shaping the bubbles. These powerful magnetic structures can control the movement of particles within the bubbles, influencing the way cosmic rays travel through the Milky Way. This hidden magnetic force might be responsible for keeping the bubbles so well formed and symmetrical, even in the middle of galactic chaos. Speaking of cosmic rays, the Fermi bubbles could be working as cosmic ray accelerators. These are particles traveling near the speed of light that zip across the galaxy. The bubbles could be helping to push these high-energy particles into motion, accelerating them to incredible speeds. Understanding this acceleration could help explain how cosmic rays behave, not just in our galaxy, but across the universe. Scientists haven't only been looking at our galaxy. By studying similar bubbles in other galaxies, they can see what's unique about the Fermi bubbles. And it turns out they're quite distinct. Other galaxies show outflows of energy from black holes or starbursts, but the size, shape, and intensity of our galaxy's bubbles stand out. The Fermi bubbles seem to be a special case, raising questions about what makes our Milky Way different. The mysteries of dark matter might also be tied to the Fermi bubbles. While no definitive proof exists, some researchers wonder if dark matter annihilation could be part of the bubble's gamma-ray emissions. Dark matter, which makes up a large portion of the universe but remains unseen, could potentially interact in ways we're only beginning to understand. If the Fermi bubbles are involved in this process, they might unlock some answers to one of the universe's biggest mysteries. The Bootes Void, an enormous cosmic empty space. Spanning approximately 330 million light-years, it is one of the largest known cosmic voids, a vast region remarkably devoid of galaxies compared to its surroundings. Discovered in 1981 through meticulous galaxy surveys, this enormous expanse revealed an unusual emptiness in what should have been a denser cosmic area. The Bootes Void's origins are linked to the early stages of the universe. Scientists believe that cosmic inflation, a rapid expansion that occurred shortly after the Big Bang, might explain its formation. This period of expansion could have created vast empty regions like the Bootes Void, where matter was less concentrated. Instead of a slow, gradual emptying, the void's size hints at an imprint left by the universe's formative stages. One intriguing aspect of the Bootes Void is its unusual gravitational effects. The void's low density impacts how light bends around it, leading to strange observations of distant cosmic objects. This distortion can provide insights into how cosmic voids influence light bending and the distribution of dark matter. Could this be an opportunity to learn more about the mysterious nature of dark energy? The immense scale of the Bootes Void might offer new perspectives on how dark energy, the force driving the universe's accelerated expansion, interacts with cosmic structures. The Bootes Void also plays a significant role in shaping the cosmic web. Its presence disrupts the typical distribution of matter and energy, affecting how large-scale cosmic structures form and evolve. Studying how the Bootes void interacts with its surroundings helps scientists understand the dynamics of cosmic voids and their impact on galactic formation. These voids are not merely empty spaces. They are crucial in shaping the structure of the universe. Another noteworthy feature of the Bootes void is its rarity in terms of large-scale structures. Unlike many other cosmic voids that often contain galaxy superclusters, the Bootes void is distinctive for its almost complete absence of such formations. This stark lack of galactic content emphasizes its status as a supervoid, highlighting its unique nature in the vast cosmic landscape. Deep field surveys and precise galaxy redshift mapping have provided detailed views of the void and its surroundings. These methods allow scientists to gain unprecedented insights into the void's structure and its role in the broader cosmic web. For example, gravitational lensing, where massive objects bend light from objects behind them, has helped map dark matter in and around the void. This technique reveals how dark matter interacts with such vast, empty regions, offering clues about its elusive nature. When astronomers first identified this massive void, the concept of voids in the universe was still in its early stages of understanding. The Bootes void's sheer size and the absence of expected cosmic structures in such a vast region sparked intense debate and curiosity. This anomaly challenged previous theories about cosmic voids and prompted a re-evaluation of how these empty regions fit into the broader picture of the universe's structure. What makes the Bootes void particularly intriguing is its colossal size combined with a nearly complete lack of galaxies. Unlike other voids that might contain sparse galactic formations or structures, this void stands out due to its almost total emptiness. This rare characteristic offers new insights into void formation and has led scientists to revisit and update their models of cosmic evolution. The Bootes void has become a pivotal example in studying how cosmic voids impact the distribution and growth of galactic structures, reshaping our understanding of the universe's large-scale organization. The Methuselah star, oldest known star. The Methuselah star, officially known as HD 140283, has intrigued astronomers with its mysterious age and what it reveals about the early universe. Nestled in the constellation of Hydra, about 190,000 light-years away, this star belongs to an ancient group called Population 2 stars. These stars are some of the Milky Way's oldest inhabitants and provide a unique window into the universe's early stages. What sets the Methuselah star apart is its initially estimated age, which seemed to challenge our understanding of cosmic history. For a time, it was thought to be around 16 billion years old, a number that initially surpassed the universe's accepted age of approximately 13.8 billion years. This age discrepancy ignited debates among scientists, leading to a re-evaluation of both the star's age and our cosmic timeline. To determine a star's age, astronomers use the Hertzsprung-Russell diagram, which plots stars based on brightness and temperature. Typically, older stars have fewer heavy elements, because they were formed before these elements were widely spread throughout the universe. The Methuselah star's low metallicity, which means it has fewer of these heavy elements, fits its classification as an ancient star. However, this low metallicity, coupled with its age, presented a puzzle. One explanation for this discrepancy involves revising our stellar evolution models. The characteristics of the Methuselah star, its brightness and temperature, might suggest a different path of evolution than previously thought. This could imply that the star isn't as old as originally estimated, or that its development involves more complexity than our models accounted for. Another possibility is that the methods used to estimate the star's age could have contained errors. With advancements in technology, more precise measurements have since adjusted the star's age to about 13.7 billion years. This new estimate aligns better with the age of the universe, resolving the earlier confusion. Beyond its age, HD 140283 provides crucial insights into the early universe and the formation of galaxies. As a representative of some of the universe's first stars, known as population 3 stars, it helps scientists understand conditions in the cosmos shortly after the Big Bang. These primordial stars were massive and short-lived, and they produced the heavy elements that later contributed to the formation of galaxies and planetary systems. Population 3 stars were the universe's first generation of stars, born from the primordial gas that existed after the Big Bang. Their fusion processes created the heavy elements that are essential for forming subsequent stars and galaxies. By studying ancient stars like the Methuselah star, scientists can glean more about these early conditions and the evolution of the universe from its infancy to its current state. The Methuselah star also connects to broader cosmic topics, like the Fermi bubbles, which offer clues about galactic dynamics, and the Buta's void, which sheds light on cosmic structures. This ancient star enriches our understanding of stellar evolution and the universe's history. It highlights the importance of studying ancient celestial objects to piece together the cosmic timeline and grasp how various phenomena have shaped the universe over billions of years. As scientific tools and models evolve, our grasp of the universe deepens. Discoveries like the Methuselah star emphasize the need to refine our knowledge and explore new research avenues. By examining ancient stars and other celestial objects, scientists enhance our appreciation for the universe's intricate processes and remarkable design. Why did the Methuselah star initially appear older than the universe? The star's initial age estimate was based on its brightness and temperature, which seemed to suggest it was around 16 billion years old. This conflicted with the universe's age of 13.8 billion years. The discrepancy led scientists to revisit both the star's characteristics and the methods used to estimate its age, resulting in a revised age that aligns more closely with the universe's age. What does HD 140283 tell us about the formation of the first galaxies? The Methuselah star is part of a group of stars that formed shortly after the Big Bang. Studying this star provides insights into the conditions of the early universe and the processes that led to the formation of the first galaxies. By understanding ancient stars, scientists can better comprehend how the first heavy elements were created and how they contributed to the development of galaxies and planetary systems. Hani's Vorwerp, the galactic phantom. Hani's Vorwerp is one of the universe's most unusual and intriguing objects, offering a unique glimpse into cosmic phenomena. Discovered by Dutch amateur astronomer Hanny van Arkel in 2007 while examining data from the Galaxy Zoo project. This object stands out due to its striking appearance and the mysteries it holds. Situated about 650 million light-years away from Earth, Hani's Voorwerp, which means Hani's object in Dutch, is a large greenish-blue cloud of gas and dust located near the galaxy IC 2497. This object is part of a broader cosmic enigma that has captured the attention of astronomers and scientists. The cloud's bright green color, seen in optical light, is due to the emission lines of doubly ionized oxygen, which makes it a vivid and unusual sight in the vastness of space. Hani's Voorwerp is classified as a type of ionized gas cloud, or HII region, but what makes it special is its unusual association with the nearby galaxy IC 2497. Observations reveal that the cloud is connected to a past event involving the galaxy's active nucleus. The central region of IC 2497 is home to a supermassive black hole, which at some point in the past was actively feeding on matter. This feeding process, known as an active galactic nucleus, AGN phase, emitted powerful radiation that ionized the surrounding gas, creating the striking appearance of Hani's Voorwerp. One of the most intriguing aspects of Hani's Voorwerp is its relationship with the galaxy IC 2497. The cloud's appearance that it is a remnant of a past AGN phase, where intense radiation from the black hole energized the gas and caused it to emit light. However, current observations indicate that IC 2497's nucleus is no longer in this active phase. The discrepancy between the cloud's brightness and the galaxy's current state has led scientists to investigate what might have caused this prolonged afterglow. The discovery of Hani's Voorwerp has also led to fascinating discussions about the processes that drive the activity of supermassive black holes. It raises questions about how long such ionized clouds can persist after the AGN phase has ended, and what this means for our understanding of galaxy evolution. This object serves as a cosmic time capsule, providing clues about the past behavior of galaxies and the dynamics of their central black holes. Hani's Vorwerp is part of a larger cosmic puzzle involving similar ionized gas clouds. Observations of other galaxies have revealed similar structures, known as ionization cones, or ionization blobs, which share characteristics with Hani's Vorwerp. These structures offer valuable insights into the interactions between galaxies and their central black holes, helping astronomers piece together the history of galactic evolution. What makes Hani's Vorwerp particularly fascinating is the combination of its unusual appearance and its connection to the galaxy's history. The greenish hue of the gas cloud, combined with its association with a past AGN phase, makes it a visually stunning and scientifically significant object. This vivid color, resulting from the emission lines of doubly ionized oxygen, highlights the complex interplay between radiation, gas, and dust in the universe. Additionally, Hani's Vorwerp prompts questions about the nature of cosmic feedback mechanisms. How do these ionized gas clouds form, and what role do they play in the evolution of galaxies? The study of such objects can shed light on the processes that regulate the growth of supermassive black holes and the impact of their activity on their surrounding environments. Linking back to other fascinating cosmic objects, such as the Brightest quasar and Sagittarius A asterisk, Hani's Vorwerp provides yet another crucial piece in understanding the universe's grand design. The Brightest quasar, known for its extreme luminosity and distance, showcases the intense power and activity that can occur in the early universe. Similarly, Sagittarius A asterisk, the supermassive black hole at the center of our Milky Way, offers insights into the behavior of black holes and their influence on their surrounding galaxies. In this context, Hani's Vorwerp emerges as a unique example of how these cosmic phenomena interact over time. While the Brightest quasar highlights the vigorous activity of distant galaxies, and Sagittarius A asterisk demonstrates the ongoing influence of a supermassive black hole within our own galaxy, Hani's Vorwerp represents the aftermath of such activity, a gas cloud illuminated by the radiation of a now quiet galactic core. Just as the Fermi bubbles and the Bootes void provide valuable information about cosmic processes and structures, Hani's Vorwerp helps us understand the enduring effects of active galactic nuclei and their capacity to shape and illuminate their environments. SN 2006 GY, the brightest supernova. SN 2006 GY is a fascinating example of a supernova that defies the usual patterns seen in these cosmic events. Discovered on September 18, 2006, SN 2006 GY stands out for its incredible brightness, reaching about 50 times that of an average supernova. But what makes SN 2006 GY truly remarkable is how its interaction with pre-existing circumstellar material profoundly affects its characteristics. The supernova's exceptional luminosity wasn't solely due to the explosion itself. Instead, it was significantly amplified by a dense ring of gas that surrounded the star before it exploded. This gas shell, expelled by the star in the lead-up to the supernova, played a crucial role in the bright display. The dense material around SN 2006 GY interacted with the explosion's energy, resulting in a light curve that showed a slower, more gradual decline in brightness compared to typical supernova. This slower decrease highlights how the dense gas and dust around the supernova influenced its light, challenging simpler models of how these cosmic events behave. Another intriguing aspect of SN 2006 GY is its unusually high gamma-ray emissions. Unlike other supernovae, which might produce gamma rays associated with gamma-ray bursts, SN 2006 GY's gamma rays were exceptionally. This high gamma-ray output suggests an extraordinarily energetic explosion. The question arises, how does the interaction with pre-existing material influence both the brightness and gamma-ray production of a supernova? The answer lies in the complex dynamics between the supernova's explosion and the surrounding gas shell. This interaction enhances the brightness and alters the gamma-ray emissions, offering a new perspective on the mechanisms driving these cosmic events. The progenitor star of SN 2006 GY was a massive one, estimated to be between 20 and 30 times the mass of our Sun. Such massive stars undergo significant changes before they explode, shedding their outer layers and creating a dense gas shell. The mass loss from the star and the subsequent interaction with this surrounding material were key factors in the supernova's extreme brightness and high-energy emissions. This detailed interaction provides valuable insights into the end stages of massive stars and how their explosions can differ from more typical supernovae. Spectroscopic studies revealed unique emission profiles in SN 2006 GY. These profiles, linked to the interaction with the dense gas shell, shed light on the supernova's internal processes and challenge existing models. By examining these emission patterns, scientists gain a deeper understanding of the physical conditions during the explosion, refining our knowledge of supernova mechanics. SN 2006 GY's discovery has also influenced how supernovae are classified. Its distinct features, such as the interaction with circumstellar material and unusual gamma-ray emissions, have led to a re-evaluation of supernova categorization. This reclassification process is crucial for improving how scientists study and understand these powerful cosmic events. FRB 121102, the repeating fast radio burst. Fast radio bursts, FRBs, have fascinated astronomers with their brief yet intense flashes of radio waves. Among these cosmic signals, FRB 121102 stands out, earning the nickname Cosmic Repeater due to its remarkable ability to emit repeated bursts. Discovered on November 2, 2012, this FRB is different from others primarily because of its repeating nature. But what makes FRB 121102 so unique? First, FRB 121102's emission patterns are far from ordinary. Unlike other FRBs that might show random or single bursts, FRB 121102 displays complex and distinct patterns. These patterns aren't just random, they are influenced by its environment in ways that are still being deciphered. Researchers have observed that the bursts from FRB 121102 don't follow a simple, repetitive rhythm, but occur in irregular clusters. This complexity suggests that local conditions in its host galaxy might be playing a significant role in how and when these bursts are produced. The host galaxy of FRB 121102 is another aspect that sets it apart. It's located in a dwarf galaxy known for its high rate of star formation. This galaxy is not just any ordinary galaxy, but one with intense and rapid starbirths. The dense and dynamic environment might be crucial in generating the repeating bursts. It's possible that the high levels of stellar activity contribute to the unusual behavior of FRB 121102, making its study even more intriguing. The bursts from FRB 121102 are not emitted at regular intervals, but rather in intricate clusters. This irregularity indicates that the mechanism behind these bursts is more complex than simple periodicity. Researchers are investigating whether these patterns are related to the specific conditions of the host galaxy, or if they are influenced by other cosmic events, such as nearby supernovae or gamma-ray bursts. Interestingly, there's also a potential connection between FRB 121102 and high-energy phenomena within its host galaxy. Some studies suggest that the bursts might be linked to remnants of supernova or even gamma-ray bursts. If true, this connection could provide clues about how different high-energy events might interact with and influence FRBs. The presence of high-energy processes could be contributing to the unique characteristics of FRB 121102, making it a valuable object for understanding the interplay between various cosmic phenomena. The dense material surrounding FRB 121102's host galaxy might also be playing a role in shaping the bursts. This material could be interacting with the radio waves in ways that affect their emission and behavior. For instance, interactions with surrounding gas and dust could cause variations in how the bursts are observed. This aspect of FRB 121102 emphasizes the importance of the local environment in influencing the nature of cosmic signals. FRB 121102 brings a fresh perspective to the study of cosmic signals with its distinct behavior and features. While pulsars and supernovae are extensively researched and understood, FRB 121102 stands out due to its recurring bursts and intricate emission patterns. These characteristics challenge our current models and highlight gaps in our understanding, suggesting that existing theories may need significant revision. Investigating FRB 121102 not only advances our grasp of repeating FRBs, but also sheds light on the broader spectrum of cosmic signals. Each new observation helps refine our comprehension of how the universe behaves and how different cosmic processes are interconnected. The ongoing research into FRB 121102 could reveal new and surprising aspects of FRBs, deepening our insight into these mysterious signals and their relationships with other cosmic phenomena. GRB 080319b, the brightest gamma-ray burst. Gamma-ray bursts, GRBs, are some of the most dramatic and energetic events observed in the universe. Among these, the GRB 080319b, also called the cosmic flashbulb, stands out for its extraordinary brightness. Detected on March 19, 2008, the cosmic flashbulb is the most luminous gamma-ray burst ever recorded. This exceptional burst offers a unique opportunity to delve into the extreme processes that power these cosmic explosions, providing vital insights into the universe's most intense phenomena. Gamma-ray bursts are short, intense flashes of gamma rays, the highest energy form of electromagnetic radiation. They occur when massive stars collapse or when neutron stars collide, unleashing massive amounts of energy in mere seconds. The cosmic flashbulb is notable not just for its energy, but also for its unprecedented visibility. It was the first GRB with an optical afterglow, bright enough to be seen with the naked eye, a rare feat given the vast distances involved. Originating from a galaxy about 7.5 billion light-years away, the cosmic flashbulb offers a glimpse into the universe as it was billions of years ago. Despite its immense distance, the burst's extraordinary brightness allowed astronomers to observe it in detail, which is a significant achievement since most GRBs are too faint or too far away to be studied this closely. The optical afterglow of the cosmic flashbulb was bright enough to be detected without advanced equipment. This rare visibility enabled astronomers to capture detailed images and spectra, providing rich data about the burst and its aftermath. Observations were made across various wavelengths, including optical, X-ray, and radio, which revealed detailed information about the burst's behavior and its interaction with surrounding material. The study of the cosmic flashbulb has led to several important findings. The burst released energy far surpassing that of typical supernova and other cosmic explosions, highlighting the extreme power of gamma-ray bursts. Additionally, the event provided insights into the conditions within distant galaxies, helping to paint a clearer picture of the universe's evolution. Technological advancements have significantly contributed to the study of the cosmic flashbulb. Improved telescopes and data analysis techniques have enabled more detailed observations of high-energy phenomena. These advancements have enhanced our ability to detect and analyze gamma-ray bursts and other cosmic events. The afterglow of the cosmic flashbulb was studied across multiple wavelengths, which helped to unravel the burst's complex behavior. Optical observations provided data on the light curve and spectral properties, while X-ray and radio observations offered additional insights into the burst's emission and evolution over time. This comprehensive approach allowed scientists to build a more complete understanding of the burst's characteristics. The host galaxy of the cosmic flashbulb, known for its high levels of star formation, aligns with the expected conditions for long-duration GRBs. This connection helps link GRBs with specific types of galaxies and star-forming regions, shedding light on the broader cosmic processes involved. By studying the environment of the cosmic flashbulb, scientists gain insights into the conditions that lead to such powerful explosions. The cosmic flashbulb contributes a unique perspective to our exploration of cosmic phenomena. While earlier discussions covered objects like pulsars, black holes, and supernovae, the cosmic flashbulb highlights the most energetic bursts in the universe. This event enriches our understanding of extreme cosmic processes and the diverse events that shape the cosmos. The power and intensity of gamma-ray bursts are vividly demonstrated by the cosmic flashbulb. This burst has provided crucial insights into the mechanisms behind these events and the conditions in distant galaxies. The advancements in observational technology driven by the study of the cosmic flashbulb have deepened our understanding of these enigmatic cosmic phenomena, bridging past discoveries with new knowledge about the universe's most intense events. In exploring the strangest objects in the universe, from the Methuselah star's baffling age to SN 2006 GY's record-breaking brightness, we've unraveled mysteries that challenge our understanding of time, space, and stellar evolution. Each discovery sheds light on the complex processes governing the cosmos, from the formation of ancient stars to the violent ends of massive ones. These objects remind us that the universe is filled with phenomena that continue to intrigue, provoke, and push the boundaries of what we think we know about the cosmic expanse. I hope you enjoyed this journey. If you did, feel free to subscribe to the channel. Thanks for watching.